Have you ever wondered why something as tiny as an atom can produce so much energy when it splits? That's right, we're talking about atomic energy, an incredible force that's both perplexing and fascinating. To understand atomic energy, we first need to grasp the structure of the atom. Picture the atom as a miniature solar system. At the center, or nucleus, we have protons and neutrons. Orbiting around this nucleus, much like planets around the sun, are the electrons. So what is atomic energy? Essentially, it's the energy that holds these protons, neutrons, and electrons together within an atom. It's akin to the gravitational force that keeps planets in their orbits. This energy is immense, considering the force needed to maintain this atomic structure. The importance of atomic energy cannot be overstated. It's the power behind the sun's heat, the source of nuclear energy, and the force that gives life to the stars. It's the energy that powers our modern world, from electricity generation in nuclear power plants to medical treatments in hospitals. Yet it's not just about the energy that's being held within the atom. It's about the energy that can be released when these atoms are split apart. When an atom splits, the energy holding the atom together is released. This is known as nuclear fission, and it's the principle behind atomic bombs and nuclear power plants. The splitting of an atom releases a tremendous amount of energy. To put it in perspective, the energy released from splitting a single atom is about 1,000,000 times greater than the energy released in a chemical reaction, such as the burning of coal, oil, or gas. The power of atomic energy is immense, yet it's derived from something so small it's nearly invisible to the naked eye. This paradox is what makes atomic energy such an enigma, a mystery that scientists have been trying to unravel ever since the atom was first discovered. So, at the heart of it all, atomic energy is the energy that holds an atom together. But how does it work? Let's delve deeper. Imagine a tiny, tiny particle, an atom, splitting apart. But what triggers this splitting? And why does it release so much energy? Let's take a journey into the atomic world. Picture an atom, the smallest unit of matter. At its core, or nucleus, are protons and neutrons, bound together by the strong nuclear force, one of the 4 fundamental forces of nature. Surrounding this nucleus are electrons, zipping around in an electron cloud. Now here's where the magic happens. When an atom absorbs a stray neutron, it becomes unstable. This instability triggers what we call nuclear fission, or the splitting of an atom. The neutron is absorbed into the nucleus, causing it to become so unstable that it splits into 2 smaller atoms, or fission fragments. But wait, there's more. When the atom splits, it doesn't just form 2 smaller atoms, it also releases additional neutrons. These newly freed neutrons can then go on to be absorbed by other atoms, causing them to split and so on. This is the beginning of a chain reaction. Each time an atom splits, it releases energy. You might wonder why. Well, it's all about the binding energy, the energy that holds the nucleus together. When an atom splits, the binding energy that was holding the nucleus together is converted into kinetic energy and radiation. This conversion follows one of the most famous equations in physics, E equals mc2, which tells us that energy, E equals mass, m, times the speed of light, c squared. This equation shows us that a small amount of mass can be converted into a large amount of energy. This energy release is what makes nuclear fission so powerful. One single atom splitting apart can trigger a chain reaction that releases a staggering amount of energy. So, in essence, one tiny atom splitting apart can set off a chain reaction that releases a staggering amount of energy. This is the power of the splitting atom. But why does an atom splitting apart release such a vast amount of energy? This question has puzzled many brilliant minds for centuries. The answer, however, lies in a simple yet profound equation proposed by the genius Albert Einstein, E mc squared. Let's break it down, shall we? E stands for energy, m represents mass, and c is the speed of light, which is a mind-bogglingly large number. Now, the equation tells us that energy is equal to mass times the speed of light squared. What it essentially means is that mass can be converted into energy, and a small amount of mass can produce a massive amount of energy, thanks to the speed of light squared being an incredibly large number. But how does this relate to an atom splitting apart? When an atom splits, it breaks down into smaller particles. Interestingly, the mass of these resulting particles is slightly less than the original atom. This may seem counterintuitive at first. After all, shouldn't the mass remain the same? Well, not exactly. It's this tiny mass difference known as the mass defect that gets converted into energy. And remember, because of Einstein's equation, even a minuscule amount of mass can be converted into a vast amount of energy. This is precisely why the splitting of a single atom can release such a large amount of energy. It's all about the conversion of a tiny bit of mass into energy. But there's more to the story. The energy released isn't just a random burst, it's a highly specific and controlled process that depends on the type of atom and the way it splits. It's this precision and control that make atomic energy so powerful, and at the same time so challenging to harness. So the secret behind the enormous energy release is the conversion of a tiny bit of mass into energy. Fascinating, isn't it? Now that we understand why atoms produce so much energy when they split, what does this mean for us? The applications of atomic energy are vast and varied. One of the most well-known uses is in nuclear power plants. These facilities harness the immense energy produced by splitting atoms to generate electricity. This process, known as nuclear fission, involves breaking apart an atom's nucleus, releasing a massive amount of energy. This energy is then used to heat water, creating steam that spins a turbine and generates electricity. Nuclear energy is a powerful resource, capable of producing large amounts of electricity without the carbon emissions associated with fossil fuels. But atomic energy isn't just about power production. It also has significant applications in medicine. For example, radioisotopes, unstable atoms that emit radiation, are used in both diagnosis and treatment of various diseases. They can be used to create detailed images of the body's interior, target and destroy cancerous cells, and even relieve pain from certain types of bone cancer. However, the power of atomic energy is not without its perils. The same process that fuels nuclear power plants can also be used to create devastating weapons. The destructive power of nuclear weapons, as seen in the bombings of Hiroshima and Nagasaki during World War II, is a stark reminder of the potential dangers of atomic energy. Moreover, the production of nuclear energy produces radioactive waste, a byproduct that remains hazardous for thousands of years. Managing this waste and ensuring it doesn't harm people or the environment is a significant challenge. So, atomic energy, a powerful tool when harnessed correctly, but also a potential danger. It's a delicate balance. As we move forward, it's critical that we continue to explore safe, sustainable ways to use this incredible source of energy, while also mitigating its risks. It's a daunting task, but one that holds the promise of a cleaner, more efficient energy future. So, atomic energy, a powerful tool when harnessed correctly, but also a potential danger. It's a delicate balance. So, where does the future lie for atomic energy? As we cast our gaze into the crystal ball of scientific progress, we see an exciting panorama unfolding. The atomic age, far from being a relic of the past, is poised to enter a new era of innovation and development. One of the most promising avenues lies in the realm of nuclear fusion. Unlike the splitting of atoms we've discussed so far, fusion is about bringing atoms together. It's the process that fuels the sun and the stars, and if we can harness it here on Earth, it would provide a nearly inexhaustible and clean source of power. Worth noting is the ITER project, a multinational collaboration aimed at building the world's largest tokamak, a device designed to contain the extreme conditions necessary for fusion. Another burgeoning area is the development of safer, more efficient nuclear plants. We're talking about Generation 4 reactors that are designed to be practically meltdown-proof, and small modular reactors that offer flexibility and scalability. These advancements are not just about producing more power, they're about doing it in a way that mitigates the risks associated with nuclear energy. Yet with great power comes great responsibility. As we strive to unlock the atom's full potential, we must also be mindful of the challenges that lie ahead. We're dealing with a force that, if mishandled, could have catastrophic consequences. Therefore, the future of atomic energy isn't just about technological advancements, it's about regulation, oversight, and education. It's about ensuring that we use this power wisely and responsibly. In the end, the atom is a testament to the paradox of nature. Something so small can hold such immense power. Yet, it is this very paradox that makes the future of atomic energy so compelling. As we move forward, it's crucial to understand and respect the power of the atom. After all, it's a small particle with enormous potential.